My name is David Barreto, and today I want to talk about how wallet addresses are created in Bitcoin. In a previous video, we discussed how to create a public and a private key using elliptic cryptography. If you would like to know more or to refresh your memory, make sure to watch that video first by clicking on the link above. Back to our presentation. This is how a public key looks like in its hexadecimal format. You can tell it's hexadecimal because the value starts with the symbol 0x or 0x. A public key has 66 hexadecimal symbols and has a size of 33 bytes. Every time we make a transaction, the ledger will need to store the public key of the sender and the public key of the recipient, each with a size of 33 bytes. If we assume that the amount field might take 64 bits or 8 bytes, as in the case of Rust, to store a floating number, each transaction could have a size of at least 74 bytes. And I say at least because more information is added to a regular transaction. We will explore this topic in another video. 74 bytes doesn't sound like much, but remember, there are millions of transactions already in the blockchain, and that information needs to be synchronized across all nodes in the network. Just so you know, and have an idea of how massive the blockchain is, as of November 2020, Bitcoin's blockchain is 360 gigabytes in size. It's important then to optimize every single byte. So it begs the question, can we save on storage while still preserving security? To recap, a public key is derived from a private key by using elliptic curve digital signature algorithm, or ECDSA for short. As mentioned before, the public key is 33 bytes or 264 bits in size. This means that there are 2 to the power of 264 possible public keys. This number is roughly a 3 followed by 79 zeros. This also means that in order to guess a private key based on its public key, a hacker might need to try, in a worst case scenario, 3 multiplied by a 1 followed by 79 zeros possible combinations. Just so you have an idea of how massive this number is, it is believed that there are 10 to the 80 or a 1 followed by 80 zeros atoms in the whole universe. And look how close those two numbers are. In security, it's important to have a healthy dose of skepticism and to wear a tinfoil hat once in a while to prepare for worst case scenarios. What if we discover in the future that there is a problem with the ECDSA algorithm and it becomes possible to create the opposite algorithm to find the private key associated with a public key? Even worse, what if a backdoor was introduced in the algorithm in the first place by a national security agency to weaken it? Protecting the private key is of paramount importance in any blockchain. One solution to this problem is, instead of registering public keys directly on the blockchain, is to register the hash of the public key. For this purpose, we can use the SHA-256 algorithm that has been proven to be very strong. The output of the SHA-256 function is a hash of 32 bytes or 256 bits. This means that there are a total of 1 followed by 77 zeros possible combinations of hashes that can be created. These are slightly less combinations than using the public key directly, but it's still an astronomically large number. But what if there's also a problem or a backdoor in the SHA-256 algorithm? Do you know who designed this hash? The NSA. So it's not a stretch of imagination to think that a backdoor exists so they can tap into encrypted communications at their will. Satoshi Nakamoto was probably well aware of this situation and decided to add another hash into the mix, in this case, one that might be outside of the NSA's control, as it was developed in Europe and not in the US. The RIPE-MD160. RIPE-MD160 creates a hash of 20 bytes or 160 bits in size, which translate to, in 1.5 multiplied by a 1 followed by 48 zeros, possible combinations as its output. The result of hashing the public key twice, once using SHA-256 and then using RIPE-MD160, is known as the public key hash or PKH. You might question RIPE-MD160's integrity as we did with SHA-256, but because we are using both and the intermediate step is not published on the blockchain, those possible weaknesses or backdoors will become harder if not impossible to exploit. One thing that is certain is that RIPE-MD160 creates a hash that is more susceptible to brute force attack when compared to SHA-256. This is evident when you compare the possible number of combinations of both hashes. A 1 followed by 48 zeros is a significantly smaller number than a 3 followed by 79 zeros. Still, a 1 followed by 48 zeros is a huge number, and in practice, no collisions have been found for RIPE-MD160. In short, a public key hash consists of 40 hex digits or 20 bytes and are used to identify the origin and destination of every Bitcoin transaction. Once again, the blockchain doesn't record a user's public key. The blockchain records instead the user's public key hash. This is done to further protect the private key and to reduce the size of every transaction. Now that we know how PKH or public key hashes are created, let's see how they can be used. Let's say, for example, that John sends a message to Mark requesting 0.1 Bitcoin for whatever reason. John will of course include his own public key hash, so Mark can use it as the destination of the funds. So Mark agrees, goes to his wallet software and starts typing the destination PKH. Sadly for him, he makes a typo and instead of a 7, he writes an 8 for one of the hex digits. When he clicks send, the money is sent to that PKH that is not associated with John's private key. In fact, it's almost guaranteed that no other person has a private key associated with that PKH, given how many possible combinations there are when using hashing, as we discussed in the previous slide. This is known as burning Bitcoin, as the money cannot be retrieved. Ideally, our wallet software should be able to prevent these silly mistakes while creating a shorter version of an address that is future-proof so different formats can emerge over time. To solve these issues, Bitcoin wallets encode our public key hash using a base58 check encoding. Let's see how it works and how it solves all of the problems mentioned before. We're going to start with the public key hash because that's the information that is actually stored on the blockchain. The diagram that I'm about to show you comes from the book Grokking Bitcoin that I can highly suggest as it has been a great source of information. First, we're going to prepend a version number to our public key hash as the first byte of our hex number. This version allows for future-proofing wallet addresses format, as different versions can coexist and are easily identifiable just by looking at the first byte. For now, let's use 0 as this is the original format. If you're wondering why 2 zeros are present in the hex number and not just the one, it's because we are using a full byte to store the version, and a byte can accommodate 2 hex numbers, thus the 2 zeros that you see there. Next, we are going to calculate what is called a checksum to detect when we make silly typos as in the example before. The checksum is calculated by hashing twice our hex number using the SHA-256 function and then taking the first 4 bytes of the output. We are now going to append this checksum at the end of our hex number, and finally, we encode this hex number as a string using the base58 encoding scheme. The result is a format that we normally associate with a wallet address. Comparing the initial public key hash with the wallet address, we can see that the former consists of 40 hex digits, while the latter consists of 34 characters. I think most people feel comfortable with strings, or more comfortable with strings rather than with hex, so it's a first win. The second benefit is that a wallet address has an embedded error protection mechanism in the form of a checksum. A public key hash doesn't have that feature. In a later slide, I'm going to show you how this checksum is used for detecting errors or typos. Finally, a wallet address includes a version number, so we can experiment with different formats to add new features to this identifier, the same way that we added a checksum for error protection. We briefly discussed why base58 encoding is used, mainly to transform a hex into a string. But it's not only because it's more intuitive for people to deal with strings than with hexadecimal numbers, it's also because a hex number in the wild can look like a string if not prepended by the 0x, which is just a convention, but not part of the number itself. Consider this value. Is that a strange non-English word, or is it a hex number without the 0x? Hex numbers only really make sense for machines, so they are not good candidates for wallet addresses that it's meant to be used by humans. If you have been programming for a while, especially for the web, you might wonder, why base58 and not the most commonly used base64? To understand why, let's look at all the symbols used by base64 for its output. It includes all the digits, all lowercase and uppercase letters, and the symbols plus and /. If we were to use base64 to construct our wallet address, we might get something like this. Notice the symbols highlighted in the address. Can you reliably tell if that's the number 1, an uppercase I, or a lowercase l? Or is that one a number 0 or the letter O? Depending on the font, it could be really hard to know, so the likelihood of us making a mistake when typing a wallet is quite high. Base58 is very similar to base64, but it removes from its output conflicted symbols like the number 0, the uppercase letters I and O, and the lowercase letter l. The symbols plus and / are also removed. Looking again at the example wallet address, and imagining that it was encoded using base58, we will note for sure that the symbols are the number 1 and the lowercase o. The ambiguity is removed along with the risk of making a typo. When you are ready to send Bitcoin to someone and you provide that person's wallet address, your wallet software performs the reverse operation for extracting the public key hash and to detect any possible error along the way. We start by decoding the string into a hex number using a base58 decode function. Then, knowing that the last 4 bytes are the checksum, the algorithm removes those bytes and keeps the checksum for error checking. The new hex without the checksum is double hashed again to recalculate the checksum, and both numbers are compared. If they are the same, then there's no error in the wallet address and the operation can continue. But if those two values are not the same, an error is detected and the wallet will prevent the user from using this address as an identifier for the transaction destination. Finally, if all goes well and the checksums match, the first byte storing the version is removed and we finally have a valid public key hash to use. Let's review our previous example with John and Mark once again, but this time using a wallet that implements the base58 check decoding. So this time John is sharing his wallet address instead of his public key hash with Mark. But Mark can't help it, and once again he makes a typo when entering the address in his wallet software to send the coins. Only this time his wallet is able to detect the error and prevent Mark from burning his Bitcoin. To summarize what we have learned, public key hashes are used instead of public keys to further protect private keys. Public key hashes are stored in the blockchain for every transaction. To prevent typing errors, Wallet implements base58 check encoding and decoding. Remember, Your wallet address is not your public key or even the public key hash. It is the result of applying the base58 check encoding function to your public key hash. In the next video, we're going to implement this base58 check encoding and decoding mechanism using Rust. So I'll see you later.